So let's continue our discussion on St. Petersburg's paradox. Okay. So let's review the problem again. A fair coin is tossed repeatedly until it shows heads. The casino agrees to pay the gambler $2 if a head appears on toss 1, and $4 if the first head appears on toss 2. This is 2 power 3 if the head appears on toss 3, and 2 power k if the first head appears on toss k. And we talk about the probability for the first head to appear on toss 1 is 1/2. That is the probability of head. Agree? And what's the probability that you have a tail and then a head? So you have 2 trials. The first one is tail, and the second one is head. So these 2 are 2 independent trials. So it will equals to probability tail and probability head. This will equals to 1/2 power 2. And similarly for other trials. Okay. So that's why we have 1/2, 1/2 power 2, 1/2 power 3, 1/2 power k. Now the problem is, what is the gambler's expected reward? So here, in order to get the expected reward, so this is the expected reward. So toss, we have toss n, and probability, and price. And suppose price is y. Then we will have the first toss, second toss, third one, and until to the case 1. So the probability for the head to appear in the toss 1 is 1/2, 1/2 power 2, 1/2 power 3, 1/2 power 2k. And the price is $2, $4, and $8 to 2 power k dollars. So in order to calculate the expected reward, we use the price multiplied by the probability, then we add them together. So this is what we got. So expected reward is infinity. Okay? Now, so if we have a rational gambler who, if somebody is a gambler who always want more money, right? So, but this here, expected reward is infinity. So if somebody is really has a lot of money, he has a lot of wealth, then he would enter the game for an amount less than the expected reward. If you just played it many times, and then you calculate the average. This is the average. Okay? Now, what is the paradox? Now we have the paradox. So the paradox is no gambler will agree to pay an infinite entrance fee. So in reality, few would even pay more than $25 to play. So this is a paradox. So how to solve this paradox? Why and how to solve this paradox? So this problem, St. Petersburg paradox, was proposed in early 1700 It's from Nicholas. Bernoulli. And he formulated the problem. Okay. And then he stated the problem in 1713. He stated the problem to several mathematicians. Okay, the name is, first one is Raymond. And Buffon and Gabriel Kramer and others. Okay. But so far it has nothing to do with St. Petersburg. Why do we call it St. Petersburg paradox? It's because 1738. So back then, when they want to discuss the problems and publish a paper, they have to write, okay, in paper and then mail it with letters. They have no email, okay, no electronic PDF paper publication. So that's why it takes so many years for the problem to get disseminated, and then people get started to study this problem. And in order to let more and more scientists know the problem, in 1738, Daniel Bernoulli is the brother of Nicholas Bernoulli. There are so many Bernoullis, you will see. And sometimes this Bernoulli family, they publish a lot of papers, a lot of concepts, and sometimes you will confuse who actually did this, who did that. Okay, but here, Daniel Bernoulli and Nicholas Bernoulli. So Daniel Bernoulli presented the problem to Imperial Academy of Science in St. Petersburg. Russia. So here we got the name, St. Petersburg paradox. So now his brother Nicholas presented this problem to his brother Daniel Bernoulli. And what is Daniel Bernoulli's take on this problem is the utility theory. Okay. So Daniel Bernoulli's reaction to this problem, that is, money should be valued in proportion to its something we call it marginal utility. The additional use or pleasure one can obtain from extra amount of money. So what is marginal utility? That is the additional use or pleasure one can obtain from extra amount of money. So he has a, for example, let's see, eating the ice cream. Okay. I mean, in the very beginning, the first spoon or the second spoon is pretty good, right? But if you have already taken like 32 spoons, and the person cannot enjoy it anymore. So this is called a marginal utility. Similar example, similar problem. Okay. So if we have additional, so 1 spoon, it's okay, and the 2 spoon is okay. And if this person is keep taking it, I mean, if there's 32 spoons, more than 32 spoons, and the person will cannot enjoy anymore. Okay. So an additional ice cream beyond over 32 spoons give him only the satisfaction he received from 32 spoons. Okay. So this is called saturation point of the now you see the Bernoulli family. Okay. So here, let me insert a blank page. Let me add a page. How to add a blank page? I think I need to. Blank page is right here. No, let me add a blank page. Let's go back. Okay, here's the blank page. Then, because of the Daniel Bernoulli presented this marginal utility to Nicholas Bernoulli, then Nicholas Bernoulli has a new formulation. So Nicholas Bernoulli placed 0 probability for large values of k. So he assumes such values are morally certain not to occur. So this is like we are truncating the series of expected reward. So expectation of y is actually equals to, so here is approximately 2 over 1 over 2 plus 2 square on 1 over 2 square, and then we added it to 2 power 24, 1 over 24. So beyond that, we assume the probability is 0. So we're not going to consider it anymore. So this will be $24. So here is K. So, but he thinks, oh, this is okay, but not very convincing. This formulation is much better than the infinity one. But the conclusion is, okay, should I pay $24 to play? Okay, should we pay $24 to play? And then he emailed his solution to Gabriel and Buffon and all the other scientists. Then Gabriel has another formulation that is called, we call it a diminishing marginal utility. So here, Gabriel, Kramer. So he assumes that if we have toss n probability and price, so toss you can have 1, 2, 3 to 24, 25, and he assumes this is 1 over 2, 1 over 4, 1 over 8, 1 over 2 power 24, 1 over 2 power 25. But he's changing the price. The price is 2 power 1, 2 power 2, 2 power 3. Now he's modifying this as 2 power 24, and he thinks this will saturate just like the ice cream. And if you got more than that, it's just 2 power 24 and 2 power 24. So in this case, what he gets is the expected reward. Is the summation k equals to 1 to 24, 2k 1 over 2k, plus summation k equals to 25 to infinity. This is 2 power 24 over 1 over 2k. This will equals to 25 approximately. Okay. So he says okay, and then we pay 25 to play. Then he wrote a letter and presented this solution to Nicholas Bernoulli again. And Nicholas Bernoulli say, oh, 24 now is going to 25. And then he actually discussed with Daniel again. Daniel and Nicholas Bernoulli, and they're going to talk about the problem. They respond to Gabriel in 1731, and with a new theory called diminishing marginal utility. And the paper actually published in 1738. Did you notice how many years to publish a paper? Like, you have the draft, it takes many years to publish a paper. Nowadays, the knowledge, like information, they got communicated in a much faster pace. Okay. Now, what is diminishing? Let me add another blank page. I can only add a blank page right here. So diminishing marginal utility is the Daniel Bernoulli presented a new problem called diminishing yeah.
Will we have access to the recordings for these lectures? Because I can barely keep up with the writing.
Oh, am I writing so fast? It's okay. I think that's why I'm writing on the PDF. I want to save the notes and then publish on the website. Okay?
Thank you.
Yeah, that's a very good question. So the utility is actually log n. So we're going to place a log function on the utility. So this means the marginal utility of $n of money should be measured by log n. There is a logarithm of dollar amount. So in this case, then what will be the expected reward? Which will be 1 over 2 log 2 plus 1 over 4 log 4 plus 1 over 8 log 8 plus to infinity. So this will be k equals to 1 to infinity log 2k divided by 2k. And this will become log 4. So if we look at this problem, it's like a toss n, then you have probability, and then we have price, then we have utility. So this is 1, 2, 3, and this is 1 over 2, 1 over 4, 1 over 8. So this is $2, $4, $8. And the utility will be log 2, log 4, log 8 to log 2k, 2 power k, 1 over 2 power k, and this is k. So now this is a rational gambler problem, rational gambler. And he will pay $4 entrance fee to enter this game. How much should they pay? So they have people try different formulations. When Nicholas Bernoulli presented the problem to Gabriel Buffon and his brother, so each one of them proposed a solution, and later Daniel Bernoulli and actually drafted this solution using the log utility function. And so that's a rational bank gambler. So $4 is pretty good deal, right? So if this game is over there and you pay $4 to enter the game, approximately okay, then $2 is even better. But if you want me to pay $25, that's a little bit more, right? Okay. And we talk about the Bernoulli family. Now let me show you the Bernoulli family. So here is Bernoulli family. Let me make it bigger. So because Daniel Bernoulli and his brother Nicholas Bernoulli was very happy in 1938 with this, when this paper was published. And if you're trying to get the old paper, you can still retrieve it. And for this problem, St. Petersburg paradox. So this is Bernoulli because Daniel Bernoulli solved this problem. And there's a family. And we have Bernoulli process, Bernoulli distribution. So Bernoulli family is Nicholas Bernoulli, and then you have another Nicholas, Jacob, Nicholas 1, okay, and then another Nicholas. And then you have John, and Daniel, John, Jacob, Daniel again. So that's why people sometimes get confused, because they are junior Daniel Bernoulli and the junior Nicholas Bernoulli. So there are many theories coming out of this Bernoulli family, and many of them has their own papers and the theory about the stochastic and probability. So people sometimes get confused who actually did what. But anyhow, people just summarize them as the Bernoulli family, and they did the stochastic problem. Okay, so here is the St. Petersburg paradox problem. So it's just the appetizer for this course.